Hi everyone. In this unit, we will learn about electrons, electronic arrangement, and how it is related to the properties of elements in the periodic table, and much more. So this unit will cover chapter 5, 6, and 7 of your book. In this particular video, I will be talking about the wave nature of the light, the particle nature of the light, the quantum mechanical, or not really quantum mechanical, the Bohr's model, and the atomic emission spectrum, which covers the first day assignments. So let's talk about, by the way, at the bottom is your periodic table. Let's talk about the chapter 5, starting with chapter 5, electrons in the atom. This chapter talks about the wave nature and the particle nature of light. So which light? The light that we see, the white light, or the light that comes out of the element when you heat it. So we'll talk about all that light part. This is in your book, page number 118. And let me grab my pen. So page number 118 to 121. Electromagnetic radiations, electromagnetic radiations, or EMRs, are the wave nature of the light. So this is the waves of energy that travel through the space. So it is the wave that you're talking about that travels through the space, and it's just like a regular wave, the wave of the ocean. So you have the crests and you have the troughs. So whenever we talk about a wave, there is a crest and there is a trough. So the distance between the two crests is called wavelength. Okay, this is the upside down y, just like that, and we call it lambda. So that is the wavelength, and this is the distance between this and the peak of the wave is called amplitude. But what we are going to talk about is that there is a theory that the light comes out in the form of waves. Now, where is the light coming out from? This is the nucleus, and here are the energy levels. In the last unit, we talked about the Bohr's model or the planetary model. According to the planetary model, the electrons jump from the higher energy level to the lower energy level. Okay, so when they jump from the higher energy level to the lower energy level, the extra energy, the difference between the two energies, the extra energy comes out in the form of light. Okay, and this is the light I'm talking about. So the light, there are two different theories about that light. One theory is that the light comes out in the form of waves, and one theory is that the light comes out in the form of particles. So we will discuss both right now. Right now I'm talking about the wave nature of the light. So the distance between the two crests is called wavelength, which is lambda. That is the distance between the 2 points, whether crest or the trough. We will use meters or nanometers for this. Okay, so 1 meter is 10 to the power 9 nanometers. So keep that relationship in mind, because you will be making some conversions. Now, wavelength is one terminology that you need. The other terminology is the frequency. Frequency means how many waves can pass through a point in 1 second. So if the waves are going through this point, then how many waves can pass through this point per second? Per second. The S minus 1 means per second. So the number of waves that pass through a given point per second. We use the unit hertz, or we use the unit per second. Okay, how the frequency and the wavelength are related. Now, I think this is something you can figure it out. If I have a wave of this kind, and if I have a wave of this kind, first of all, which one has a larger lambda? This has the larger wavelength, right? Compared to this, which is smaller wavelength, because wavelength is the distance between the two crests or two troughs. Now, how many waves can pass through this per second, and how many waves can pass through this per second? Of course, since I have less wavelength, I can pass more waves through this point in a second compared to this, because it has a larger wavelength. So as you see that the frequency is inversely proportional to the wavelength, like they're opposite. It's a seesaw relationship. If one goes up, the other goes down. So it's a seesaw relationship. The wavelength is inversely proportional to frequency. Inversely means opposite. One goes up, other goes down. So that's what it says here. that wavelength is inversely proportional to frequency, and to remove the proportionality sign I will use the constant, which is the speed of light. So c equals nu lambda, you know, it's not really v, it should be a cursive v. So c equals nu lambda, or lambda equals c over nu, lambda equals c over nu. Alright, this is how we can calculate the wavelength, where c is the speed of light. Okay, c is the speed of light, or speed of the electromagnetic radiation. We can imagine the speed of light, which is 3 times 10 to the power 8 meter per second. And wavelength and frequency are opposite or inversely proportional. This way, if I have the wavelength, I can calculate the frequency. If I have the frequency, I can calculate the wavelength, because I always have the c with me. So if you look at this electromagnetic spectrum, it's also given in your book. So here is the frequency. This is the frequency given in hertz, okay, and this is the wavelength given in the meters. As you see that the larger the wavelength is, the smaller the frequency is, okay, and as the wavelength increases, the energy decreases. Okay, wavelength is inversely proportional to energy. Okay, so more the wavelength is, less the energy is. So as you see, the radio waves have much less energy, but they have a bigger wavelength. This is very small wavelength, but they have high energy. The ultraviolet rays and the X-rays and the gamma rays, they have high energy waves. And in between the ultraviolet and infrared, we have the visible spectrum. Visible spectrum is called also continuous spectrum. The word continuous spectrum means that this blue blends into this color, and this color blends into this color, and green blends into yellow, and yellow blends into red. So there is no defined line. You cannot tell that where one ends and the other one starts. So this is a continuum of the wavelength. Okay, so that's why we call it a continuous spectrum, because it merges, one color or one wavelength merges into the other one. Whereas if we talk about the spectrum of an element, we will get a very defined lines, okay, and that is called line spectrum that we get for a particular element, that I will talk about later on. But I just want to share that there is a difference between the line spectrum and the continuous spectrum. But here is the electromagnetic spectrum. You know, you don't have to memorize any of this. You just need to know how to read this. You know, so these are the frequencies, these are the wavelengths. The wavelengths are increasing, the frequency is decreasing, and the less the wavelength is, the more the energy is. Okay, and more the frequency is, more the energy is, because they're opposite. You know, so here is the wave nature of the light. The light that comes out when an electron jumps from a higher energy level to the lower energy level. We talked about the wave nature of the light. So what you need to do is you need to go to the page number 121 and practice problem 1 through 4. I gave you the relationship that 1 meter equals to 10 to the 9 nanometers, or vice versa, 1 nanometer equal to 10 to the minus 9 meters. So I'm going to do one question for you, just to make sure you know how to do this question. So on page number 21 for your book, there is a sample problem. The problem says that microwaves are used to transmit the information, and what is the wavelength? You need to calculate the wavelength of a microwave which has the frequency of 3.44 times 10 to the 9 hertz or per second. You know, it is the same thing. So if I have to calculate the wavelength and I'm given the frequency, I gave you equation already, C equals nu lambda, okay, where nu is the frequency, and let me tell you what is the word that I am saying, nu, okay. So nu is the frequency, and this is the wavelength, and it is lambda. I will be using the word lambda and nu. I want you to understand what that means. So since I need to calculate the lambda, and I'm given the nu. So to calculate the lambda, I will change the equation to make C over nu, okay, C over frequency. I know that C equals 3.00 times 10 to the 8 meter per second. So let's plug the numbers in. I hope you can manage this part. That to calculate the lambda, I will do the 3.00 times 10 to the 8 meter per second divided by the frequency which was given in the question, 3.44 times 10 to the 9 per second. So per seconds get cancelled. I can take this 9 up in the numerator. It becomes minus 9, by the way. Okay, so I can solve the rest of the question. So I will have 8.72. If you use your calculator, I will have the answer as 8.72 times 10 to the negative 2 meters. Okay, let me know if you don't get this answer or if you don't understand it. So basically you plug the numbers in. You had to calculate the wavelength, frequency was given. This is the equation that we use. So to calculate the wavelength, I will do divide this by the frequency, which I did here. So I know the C, I know the frequency. You divide these two numbers. Okay, and 9 goes up there. It becomes 8 minus 9. And this is how we solve it, and seconds get cancelled, your answer will be in meters. So now I want you to go ahead and do the questions on this page from practice problems 1 through 4. Once you finish that, the next thing we want to talk about is the particle nature of light. Okay, so what I was talking about earlier, that there was a scientist, his name was Planck. He gave us the particle nature of light. He said that when an electron jumps from a higher energy level to the lower energy level, the light that comes out, it comes out in the form of particles, not the waves. And those particles are called photons, okay, or quantas. So quanta is the kind of small increment or small particle of energy, or photon is the small particle of energy that comes out. Okay, so atoms lose or gain energy in increments rather than waves, and quanta or photon is the minimum amount of energy that can be gained or lost. So to calculate the energy of that one quanta, we will take h over, the formula is h times nu, where E is the energy in the joules. Okay, we're calculating the energy. H is the Planck's constant, because Planck was the scientist who gave us this equation, and this is the value of the Planck's constant. You have to memorize it. And nu again is the frequency of that particle, the speed at which the particle is coming out. So according to Planck's constant, energy is directly proportional to that frequency. So more the frequency is, more the energy is. Okay, keep that in mind. According to this equation, energy is directly proportional to frequency. So this is much easier to calculate. Okay, so we go to page number 124 and we do practice problems of 5 through 6. But before we do that, I will do an example problem. So on page number 124, you have an example that you are given the frequency of a photon of a violet light. Okay, the tiny drops of water in the air disperse the white light of the sun into the rainbow. So the question is asking that what is the energy of a photon, okay, from the violet light, who has the frequency of 7.23 times 10 to the negative 14 per second. So you need to calculate the energy of the photon, and the formula to calculate the energy of the photon is E equals h nu. All right, it's pretty simple. I already know the h because h is Planck's constant. It is 6.626 times 10 to the negative 34 joules into seconds. So this is the unit. So I know the both things. I know the Planck's constant, 6.62 times 10 to the negative 34 joules into seconds, and I multiplied by the frequency that is given in the question, 7.23 times 10 to the negative 14 per second. Per second is like 1 second, so these seconds get cancelled. Okay, so you multiply the two numbers, and that gives you your answer as E equals 4.79 times 10 to the negative 19 joules. So this is how we calculate the energy of a photon. So I have given you two equations. One is the energy to calculate the one is to calculate the energy of the photon if you're given a frequency, and one is C equals nu lambda. If I have to calculate the energy and I'm given a wavelength, I can replace this, that E equals H C over lambda, because nu is C over lambda. From here, nu is C over lambda, so I can replace that with the nu. So if I can calculate the energy even if I'm given the wavelength, or I can calculate the energy even if I'm given the frequency. So keep this in mind, do all the practice problems, and then we move on. So atomic emission spectrum. So far we were talking about the continuous spectrum, the visible light, the one that is all merges together. But when we talk about a particular element like sodium, potassium, calcium, strontium, when we talk about a particular element, the energy that comes out when the electron jumps from a higher energy level to the lower energy level, we call the atomic emission spectrum. So each element's emission spectrum is unique. It's like a fingerprint for that element. Okay, so we can identify the element by that emission spectrum. If we look at this through a spectrometer, we see the particular defined lines, because for the element they have discrete energy levels. So either electron will jump from here to here, or it will jump from here to here. It cannot be all over the place. So when it does that, I get a very defined wavelengths, defined lines. So what happens is that I take this element, I put it on the heat, and that heat gives it energy. The electron will gain the energy to jump up to a higher energy level, but since it doesn't belong to this level, it will jump back down, and when it jumps back down, it gives out the energy, and that energy comes out in the form of atomic emission spectrum or the line spectrum. So the colored lines that I see here are from the energy emitted when the electron drops back to its ground state. Okay, ground state is the lowest energy state. Ground state means the lowest energy state. So ground state is always energy level 1. Okay, everything above energy level 1 is the excited state. So what we do is, we can do this lab sometime in the class, that we will take different elements and we put it on the flame, and we see defined colors. Like calcium gives you this kind of reddish color, potassium gives you a purple color, sodium gives you a golden color. So we can identify the elements by a particular color they give us. So we call it a flame test. Okay, and we enjoy this flame test on a very larger scale on every 4th of July. This is the chemistry behind 4th of July, that elements are taken in a larger amount and the electrons are triggered to a higher energy level by giving the energy, and when they will come back down, we see a beautiful scene on the sky. So this is the chemistry in action on 4th of July, and you must understand next 4th of July when you watch it, you must understand the chemistry behind it. So this is the atomic emission spectrum that takes care of all of the topics that were supposed to be covered in day 1. So you need to complete all of the classwork and homework practice questions that are given on the pages. All right, everybody, thank you very much.